Now let's do some problems to find the inverse from the graph. How we can find the inverse function from the graph? We're going to do some examples that how we can find the inverse of a function, the inverse function from graph when the graph has been given. So here you go for the first question, which is question number 1. My xy plane is here. This is my y equals to x. As I said, it is like a mirror. This dotted line is like a mirror. It is x equals to y. Suppose my original function is this. My inverse function is this. That's how we got the inverse function from the graph. The original function is this. I placed on the other side of the dotted line. This dotted line, as I said, it is y equals to x. It is exactly like a mirror. It behaves as a mirror. So whenever you put the function in front of this mirror, you will get the exact shape on the other side. So the shape of this function on the other side will be this. This is gonna be the inverse. It is like you place a mirror in the middle. So whatever thing you place in front of the mirror, you will get that shape inside the mirror. So that inside shape is the inverse of that thing. Suppose I place this function in front of the mirror. So I got this shape inside the mirror. This inside shape is the inverse function of that original function. This is my original function. This is going to be my inverse function. But let me extrapolate you a bit by using the coordinate points. We know that for the inverse function, the x values become the y, and the y values become the x. Let me give you a t-table here. This is my x, here is my y. Suppose my x equals to 0 and my y is also 0. So my point is here at origin, at -2 along x-axis and -1 along y-axis. My third point will be here, which is -4 along x-axis and -2 along y-axis. But the fourth point is here, which is +1. It is 1 along x-axis and 2 along y-axis. Similarly, my fifth point will be here, which is +2 along x-axis and +4 along y-axis. Look, these are just the coordinate points along x-axis and y-axis. Let me go lesser than 0. At -2, at x equals to -2, -1, -2. At x equals to -2, my y value is -1 here, -1. So at this point, I have -2 along x-axis and -1 along y-axis. My third point will be -4 along x-axis, -1, -2, -3, -4. -4 along axis, which makes the point along y-axis at -2. -1, -2. So here the coordinate point is -4 along x-axis and -2 along y-axis. But when I go more than 0, like here, at x equals to 1, my y value will be 2. At x equals to +1 here. Look, I'm talking about the original graph. I didn't touch the inverse function graph. First, I'm talking about the original graph of a function. So at +1 along x-axis here, it makes the point at +2 along y-axis, +1, +2, +2 along x-axis. Similarly, at x equals to +2, +1, +2 here. Here, it makes the point +4 along y-axis. 1, 2, 3, 4, +4. So here I have +2 along x-axis and +4 along y-axis. So these are the coordinate points for the original graph. But what about the inverse graph? Let me identify the points for the inverse graph. But now let me make the t-table for the inverse graph. Here is my x, here is my y. So at 0 along x-axis, my y value is also 0, which is at the origin. Similarly, at -1 along x-axis, my y value is +2 here. -1 along x-axis and -2 along y-axis. Similarly, my third point will be -2 along x-axis and -4 along y-axis, which is here. My fourth point will be +2 along x-axis and +1 along y-axis, which is here. My fourth point will be +4 along x-axis and +2 along y-axis, which is here. So let me compare the coordinate points of the inverse function with the original function. Look, as we have discussed in introduction, that for the inverse function, the x value becomes the y value and the y values become the x value. So here my x values are -4, -2, 0, 1, 2. But for the inverse function, these x values become the y values for the inverse. -4, -2, 0, 1, and 2. Similarly, the y values for the original function become the x values in the inverse function here. -2, -1, 0, 2, 4. They became the x values, -2, -1, 0, +2, +4. So it is the other way around for the inverse function. It is the reverse process. Whatever value you have for the x in original function, it will be the value for the y in inverse function. And whatever value you have for the y in the original function, it will be the value for the x in a reverse function. That's what inverse function means. Let's look to the graph. My origin is the same. I have 0, 0 here and also 0, 0 here. But what about -2? -2 along x-axis and -1 along y-axis for the original function. -1, -1, -2, -2. This point is at -2 along x-axis and -1 along y-axis, -1. But when it comes to inverse, this -2 becomes the y value and this -1 becomes the x value. So the adjacent point for the inverse graph is this. Look to this point. At -1 along x-axis, it makes the point -2 along y-axis. So these are two adjacent points. One is for the original function and the other is for the inverse function. Here the x value is -2, and y value is -1 at this point. But this point is at -1 along x-axis and -2 along y-axis. This -1 becomes the x value and this -2 becomes the y value for the inverse function. Similarly, when you pick the third point, which is here, in the original function, at x equals to -4, -1, -2, -3, -4, at x equals to -4, this part of the original function makes the point -2 along y-axis, -1, -2. My x value is -4 and my y value is -2. At this point, my coordinate point is -4 along x-axis and -2 along y-axis. But when you compare this point of the original function with the point of the inverse function here, it is the adjacent point. It is the adjacent point of the inverse function. Here, as we know, that this x becomes the y value and this y becomes the x value. So at x equals to -2 for the inverse, at x equals to -2, -1, -2, at x equals to -2, it makes the point -4 along y-axis, -1, -2, -3, -4, -4 along y-axis. This -2, -4 are the coordinate points for the inverse function for this point. Similarly, when you compare this point of the original function, it is at +1 along x-axis and +2 along y-axis. So at +1, it makes the point at +2. But when you compare the adjacent point of the inverse function, this adjacent point, as we know that this x becomes the y value, this y becomes the x value. So now my x is 2 and my y is 1. At x equals to +2, +1, +2. Here at x equals to +2, my y value is 1, +1. At x equals to 2, my y value is +1. Similarly, when you compare this fifth point of the original function with the inverse function, at this point my x value is 2 and my y value is 4. So at x equals to 2, +1, +2. At x equals to 2, this point makes the point along x-axis at +2. It makes the point 4 along y-axis, +4. 1, 2, 3, 4. Now, if I compare this coordinate point of the original function with the adjacent point of the inverse function. As we know that this 2 becomes the y value and this y becomes the x value for the inverse. So now my x value is 4, not 2 for the inverse. And my y value is positive 2, not 4 for the inverse function here. So at x equals to positive 4, because my x value is 4 for the inverse. So positive 1, positive 2, positive 3, positive 4. This makes the point at positive 2 along y-axis, positive 1, positive 2. That's how we can differentiate the original function from the inverse function. This is the graphical explanation. So the bottom line is that we got the inverse function here from the graph. When you place the graph in front of this mirror, which is x equals to y, we got this inverse graph of a function. That's how we can get inverse function from the graph. As we know that for the original function, my coordinate points are these. These are the coordinate points for the original function, for this function. Negative 4, negative 2, negative 2, negative 1, 0, 0, positive 1, positive 2, positive 2, positive 4. For the inverse, it will be the other way around. F of x to the negative 1 is the inverse of f of x. Look, it is not equal to 1 over f of x. This negative 1 is not the exponent. It's not the negative 1 exponent. It just shows the inverse character of f of x. So for the inverse function, all the x points of the original will be the y points, and all the y points of the original function will be the x points. Look at here, this negative 4 of x for the original function will be the negative 4 for y. This negative 2 of y will be the negative 2 for x in inverse function. Similarly here, this negative 2 becomes the y value. Negative 2 here, it is the y value. My y value is negative 1. This negative 1 y value becomes the x value, negative 1, in the inverse function. This x equals to 0 becomes y, and this x equals to 0 becomes x. Similarly, in the original function, my x value is 1. So this 1, which is the x value for the original function, becomes the y value for the inverse function. This 2 is the y value for the original function, which becomes the x value for the inverse function. Similarly, the x value for the original function is 2 here. This 2 becomes the y value for the inverse, and this 4 is the y value. It becomes x for the inverse. So we are just switching the x and y values for the original and inverse function. Now one more thing, as we have discussed in the introduction, that if the given function or the original function passes the horizontal line test. Let me try this horizontal line test. Look at here, when I tried the horizontal line test, it satisfies the horizontal line test because all the horizontal lines touch the original function only once. Like here, this line touches the function here only. The second line touches it here only. The third line touches here only. The fourth line touches here only. I'm talking about the original function. I'm not talking about the inverse function. The original function or the given graph of a function must pass the horizontal line test. So if it passes the horizontal line test, we can say that it is a one-to-one function. One-to-one function. It has only one output, not two outputs. So it is a one-to-one function. Since it passes the horizontal line test, therefore, for the inverse, these horizontal lines become the vertical lines. Why I say that the given function must pass the horizontal line test? Because ultimately, these horizontal lines become the vertical lines for the inverse function. If the original function passed the horizontal line test, it means that it passes the vertical line test for the vertical lines. These horizontal lines become vertical lines for the inverse function. Now the inverse function, to be a function, must pass the vertical lines. This line touches the inverse function graph here only, and this line touches it here. The third one touches here only. The fourth one touches it here only. Pass the vertical line test. Therefore, the inverse function, this inverse graph is a function, because as I said, that your given function must pass the horizontal line test. If it satisfies the horizontal line test, ultimately these horizontal lines become the vertical lines for the inverse function. If the original function passed the horizontal lines, it must pass the vertical lines. So I can write that inverse of this function exists. Inverse of this function exists. Why I say that inverse of this function exists? Because the graph of the inverse, this inverse graph of a function, satisfies the vertical line test. If it doesn't satisfy the vertical line test, then the inverse of the function does not exist. Since it satisfies the vertical line test, I'm talking about the inverse graph, it satisfies the vertical line test, therefore the inverse of this function, inverse of this original function exists, which is here. So the bottom line is that here I got the inverse function from the graph. When I place the original graph in front of the mirror, which is x equals to y, I got this fine graph, which is the inverse function. I got it from graph. Look, there are two different things. One is inverse relation and the other is inverse function. From the inverse relation, we mean that the inverse property of the function, inverse phenomena of the function. Inverse relation is not bounded with a given function that it must satisfy the vertical line test. When it comes to the inverse relation is just the inverse property, reverse of the given function. Let me extrapolate it graphically here. In simple words, I can say that if you place something in front of the mirror, whatever thing you put in front of the mirror, you're gonna see its shape in the opposite side inside the mirror. You just put something here, like as I have it here. I place this function, I place this graph in front of this mirror. Suppose this dotted line is my mirror. I placed this graph in front of the mirror, so I got its inverse shape inside the mirror. This is the shape of this given function. This is the shape inside the mirror for this graph. So that inverse phenomena, that inverse property is what inverse relation means. But when it comes to the inverse function is a proper function. The inverse function, to be a function, must satisfy the vertical line test, as I have it here. After inversing, if this inverse graph satisfies the vertical line test, then I can say that this is called the inverse function. In simple words, I can write that inverse of this function exists. Inverse, from inverse of this function, I mean the inverse function, not the inverse relation. Inverse relation is just the inverse phenomena of the function. I'm talking about inverse function. So I repeat it. When you look to this graph, it satisfies the inverse relation as well as the inverse function, because this inverse function is a proper function. All the vertical lines, this vertical line touches this graph, this inverse graph only here. This vertical line touches it here. This one touches it here. This one touches it here. That's why the inverse of this function, which is this, exists. The inverse relation exists, and also the inverse function exists. There are two different things. One is the inverse relation and the other is the inverse function. Inverse relation is not bounded, and the inverse graph must satisfy the vertical line test. It is not necessary for the inverse relation. It is just the inverse shape inside the mirror. For the inverse function, it has to be a proper function. So to be a proper function, it must satisfy the condition of a function. What is the condition of a function? Condition of a function is that the function must satisfy the vertical line test. Then only I can write that the inverse of this function exists. From the inverse of this function, I mean the inverse function. So here the inverse function exists because it satisfies the vertical line test.